deterministic, but it should work now.
Yes. So we are very pleased to have Felipe García-Ramos to deliver the mini course whose title is
I think just local entropy.
Local entropy theory. So this is the first part. Please.
Okay, thanks, Jonathan, and also thanks, Felix, for invitation. It's I'm very happy to spend a couple of weeks here. So I sent to Jonathan and Felix some notes. It's a survey. So it's not the final version, but I think it's pretty readable. So it's called so if but I'm happy to share a copy. So this is written by Jagiellonian and myself. So you can send me an email if you want. So let me first introduce the main objects of the mini course. So I will be working with topological dynamical systems. Which just means that X is a compact metrizable space. And T is a continuous function. And the main thing I want to talk about is topological entropy. So just for completeness, I'll define it. So we will use this is this refinement of two finite open covers, and we will also use this, which is this is the inverse of each. This is the cover given by each inverse, and then this is the number of the cardinality of the smallest subcover. alpha. And then we can define some given topological dynamical system. We define and cover finite open cover alpha. We define okay, so this measures diversity of orbits. So it's a number. This is a number between 0 and infinity, and then we have.
It can be infinity.
No, this one cannot be infinity. Once I take the supremum over all alpha, it can be infinity.
Ah, right, because alpha is finite.
Yes. This is going to be supremum over finite open covers. And now this number can be infinity. Okay, and this number is invariant on their conjugacy. Okay, all these concepts are kind of inspired by statistical mechanics, and this kind of extracts the idea of Boltzmann of measuring how many different paths the orbits can take. I would see some examples.
I don't think metrizability is needed, but something is needed. So metrizability is safe.
Yes, I mean, I mean, it's enough. Just Hausdorff, it should be enough. Like if you.
Yeah, I think I don't remember.
Yeah, I mean, the thing is, most examples are metrizable. So that's why it's safe to be. But yeah, once in a while there's non-metrizable examples that come from. I think most basic examples are metrizable, but sometimes you can build systems like there's something called like the universal minimal system. Sometimes there's natural objects that may not be metrizable. So sometimes, yeah, sometimes it's good to.
The L semigroup.
The L semigroup can be non-metrizable. So there are some things that, but for now we can. Okay, so let me see some of the. Okay. So there's a way to construct the topological system with the subshifts. So now I call it A because this is kind of like an alphabet. Then A to C. Topology. And define the shift map. Yeah. This is just moving. You have a sequence, moving the sequence one step to the left. So this is the product of compact is going to be compact and metrizable. This function is this is continuous. So in other words, C shift is a topological dynamical system, and this in particular is not that interesting, but. This is kind of like a universal model where we can do X is a subshift if X is closed and the shift of X is so in this particular case X shift is also a topological dynamical system, and actually there's a correspondence between every topological dynamical systems is conjugated. So I'm not talking about conjugacy, but it's just a natural isomorphism in topological dynamics. It's conjugate to the subshift. So in general, the way I describe subshifts is just like everything, but I am interested.
Is it really one-to-one?
Because you take the Hilbert cube to the power of Z. That's actually the universal.
Yeah. Yeah. Yeah, so.
But you can have many models, right? You can have many subshifts of these which are the same.
Yeah, you can take.
The Hilbert cube, so I take the interval to the power n and then to the power z. So my alphabet is the Hilbert cube.
For example, if you take a topological dynamical system X,
so alphabet might be
huge, of course.
Yes.
Then of course my ask I want to take just a cube, but then we know that's the mean dimension, so we like that it's not possible.
But of this class, so if so when A is finite, these examples are not exact. I mean, there are interesting examples, but they are easier to manipulate. So when A is finite, we have examples that are more manageable. I don't know how to write this. So like. So I mean, I will be I will mention examples, particularly in the case when A is finite. So sometimes we have simple examples.
If you want to confuse us, you can say then the examples are amenable, because in English, amenable means.
Yes. Like. So in particular, topological entropy is simple. So actually, let A be finite and X a subshift we have that where ln x is a set of words that appear of length n. So X consists of, so then you see all the possible words that appear in all the possible points in X, and this is ln X, and then you measure the size. So in a way it's like taking finite sections of orbits, and we are measuring how many finite sections of the orbits. Sorry, I'm missing a log. I mean, this limit always exists. These are things that I'm not saying. Okay, so in particular, so for A. The language of A to the C is just A to the n, because we have all the possible words. So this is equal to A to the n. So this implies H top. Shift is low. So I'm actually in this course, I'm not very interested in calculating values of entropy. The main thing I'm interested in is the difference between positive entropy and zero entropy. That's kind of like the main. So it's like a very raw classification of dynamical systems, but entropy exhibits different characteristics. Let's see. So in a sense, sometimes the interpretation is sometimes positive entropy is kind of like a chaos, and zero entropy is not chaos. And this is the. So I'm not very interested in like exact values of entropy, but like being able to recognize and differentiate between what positive and zero entropy means. And okay, so let's. There's a very common trick to check for positive entropy. Let me test it. This is the ith coordinate times so what does it mean? It means that two consecutive values, one of them has to be zero. So they cannot be two ones. So a typical point looks like this. Okay, and now what happens if we restrict to the set 0, 2, 4, and also the so like the even numbers we restrict here. So what kind of values we can see? And actually this is going to be why? Because okay, say I only want to look at the even numbers. I want to see what I see here, but I can always put 0 on the other positions. And then on these positions I can put anything I want. So this is this A to the Z is something what people call full shift. So this is clearly not a full shift because you cannot see, you're forbidding when you see two ones together. Nonetheless, it kind of contains a full shift. It contains a full shift in this subset. Because now here I can put anything I want. And this immediately gives us because now the language at x, this is going to be bigger than 2 to the, okay, I'll write this, but this immediately gives us positive entropy. So we have that, let's put here 2n. This is going to be bigger than 2 to the n. So this is going to give us positive. Because this is still giving us exponential growth of the. Okay, and now so it seems that having this sort of full shifts, this can help us to decide when something has positive topological entropy. What is a bit but now if this this sequence here, another important thing is that this sequence has density. If they were too separated, then it will not help. So actually, if there exists S such that so I want to measure the kind of this is called the upper density. So if the upper density is bigger than 0 and x restricted to S is some full shift, then this implies that X has positive. And the proof is kind of like very similar to what you do here. I mean, you will find you take, instead of taking the limit, you take among the elements when this is big. And then in there you will have you will see this exponential growth, so then you will be able to conclude. Okay, so this is somehow not that surprising. But what's a bit more surprising is this theorem. What's a bit more surprising is that this always happens.
Is it possible to relate the supremum over positive densities of such S with the entropy?
That's an open question.
Open question.
Mm-hmm. That's and there's a, I don't know if it's by I don't know the question. It's in the notes. It's in the survey, but there's a particular open question regarding because there's some inequality that you can check. I don't remember which one, but then if you can actually measure the entropy based on the sizes of the it's an open question, but there's some sort of conjecture So this is so every time you have exponential growth, there must be some interpolating set with positive density.
Okay, so may I have a question?
Yeah, sure.
So does it matter then that the alphabet is finite here?
So what we will see later is that not.
So it doesn't.
In some senses, in some, I mean, it depends. It depends what you want. For example, if we put the alphabet here, the alphabet is size 2 actually. If we put size 3, it doesn't mean that we will see a full shift of size 3, just a full shift of size 2. And then I will mention a result, a more abstract result where we don't use finite alphabet. So there's still, even when the alphabet is not finite, there will still be some sort of independence, combinatorial independence between regions of the space. So, I mean, the part that this is the same as this is just a coincidence for 0, 1, but there are results even for non-finite alphabets. So I will not. This is a kind of like a very. It's a combinatorial proof. I will not talk so much about the proof because I want to talk a bit more about it more general. So now what I want to do is kind of like explain the setup where the more the more general version. So this was kind of like a first. So I've seen this with Benji Weiss. I've seen this. This is common. Like he gives some idea and then he moves somewhere else, and then a lot of people work. So he just kind of puts the seed, and so there's. I think this is kind of like a first result of this type, and then I think there's been a lot of other things related. But I think that's the first result that relates entropy with what now this kind of they call it independence. Okay, so. Let's go back to general systems. Finite set. And every function. So let me write this and then I'll explain the. this is in X. Okay, let me stay here a minute. So I'm thinking, okay, this is kind of, n is kind of time, and I is like a subset of time. So you can think like weekends. And then you have two choices of what you can do on that weekend. 1 and 2. So maybe you have, I don't know, maybe you have a partner and your partner wants sometimes to go to 1 and sometimes you want to go to 2. And then this function is saying that, okay, this is the way you're going to, in this finite set, the way you want to choose if you visit 1 or 2. So for every possible way that you choose, there's going to be a point in the system that is going to satisfy exactly your choice. So it's going to be, so this is in the times f. You say, okay, I wanted 1, 1, 2, 1, 2. Okay, this can be within this set. You have a freedom, or you have like this independence. So there exists this point that is going to satisfy. Okay, so example.
Why a priori are you only considering finite sets?
I think this is the. I mean, this is this general proof that's. So I mean, right now I could define it for the whole, but. I mean, the way I'm going to state the theorem, this is because I'm not going to use. I'm going to use something stronger than open density. I'm going to use like a proportion for every possible set. But yeah, I mean, there are versions of independence where you can define it not necessarily for finite, but. The version I'm going to use uses finite subsets. Okay, let's see. For example, so I mean we already saw. So in this subshift where we forbid 1, 1. What to the set is an independent set for and this is the cylinder sets. So that is all the points that start with that have 0 in the in the 0 coordinate, and all the points that have 1 in the 0 coordinate. Okay, so here and okay, and
wait, so so independent set is not defined like a result. You can take a subset of independent set. It's still an independent set.
yes,
Okay, so
yeah,
you can think about having the biggest independence.
yes, but that's exactly what I'm going to define now.
Ah.
like this is called the independence density. So let xt be a TS and you want to pair of open subsets we say okay. So we say as positive independence density if there exists Q such that for every there exists we want this finite. There exists such that in I is an independence set or okay, and now this is why we were taking finite, because we want simply to measure proportions. So in a sense, this is stronger than the upper density, because this is saying, okay, for every set, we're going to find some subset. This and this I is for every set J, we're going to find a subset that has independence. So in some sense, this is stronger because it's going to allow us to find independence. And we're using finite sets so that we can measure this proportion directly without taking limits or lim subs or anything. We're just taking the proportion. Okay, so let me.
Wait. U1 and U2 are disjoint, right?
I mean, the interesting part is when they're disjoint.
Yeah. Don't you need to assume J is long enough?
So if it's if it's short, then J can be empty sets.
In J, I is not empty because it's bigger or equal than something positive, but it can be one.
Yes.
Can be singular. Then it's easy.
Yeah. Yeah, so if this is just size, if it's singleton, yeah. So I mean, yeah, it becomes interesting once J is large enough. It depends on Q. It will depend on Q how large you want. Yeah, because if it's just size 1, then yeah, it's. Okay, so I will not give you the okay, so and now this. Yeah. So these don't need to be open. So sometimes they will be open, sometimes they will be closed. Yeah, for this theorem, we take a topological dynamical system, disjoint, closed sets. We have that. So the open set defines the open cover defined by the complements. This has positive entropy. If and only if K1 and K2 has positive independence. So this is yeah. So this will be the version for non. We have set here. We have K1. K2. This defines an open cover with the complements. So then we can measure entropy with respect to this open cover. And there's a relationship between the entropy of the covers defined by K1 and K2 and the fact that K1 and K2 are independent, have a positive independence density.
So wait, so you change there now when you define positive independence, U1 and U2 do not have to be open.
Yeah, no, they don't have to be open.
So this entropy X, T, and the pair of sets in the definition of topological entropy. What does it mean?
So these are closed sets,
Yeah,
and they are disjoint.
Yeah.
So if I take complement, this is open set. And this is also open set, and actually the two of them, the union is, since they're disjoint.
We take any open cover by two sets. Is it okay? So
Okay, yeah,
open cover by two sets, and then we take a complement.
Yes. Okay, you can also do it the other way around. Yes.
I see.
You take any open cover, and then what has independence is the complements of the open sets. Yeah.
It's covered by two sets.
Yeah, covered by two sets. Yes. So curiously the proof for this And the proof of Wise and this proof, it had to be different.
But wait, if you would now write K1C, comma K2C, would it still be correct? I don't understand the distinction here. So you would consider instead of in the last line, you would consider the open cover.
No, here I want independence for this, for K1 and K2. So what I want is a function that chooses between K1 and K2 and that I can find points that will visit.
Because the complements have a non-trivial intersection, so it's trivial. I see.
Yes. Yeah, no, yeah, so I want to visit this, I want the independence to be in these two, that I think of them like small sets, yeah. What's called the sour? Okay, so. So the proof of the first theorem I stated uses, this is a lemma in combinatorics. This is kind of well-known result in combinatorics. And then uses measures. And that's why with measures, that's why you get like positive density. Because then you use pointwise ergodic theorem, and then you get some... yeah, unfortunately, this approach, at the time it didn't seem accessible for this more general proof. And this more general proof, they wanted for more general group actions. And there was also so they needed a new combinatorial lemma. Okay, so let me first define something. Let's finite this set. And gamma b consisting of sets of the form Okay, so think that in each coordinate we have three elements. In each and then we have this finite product, and then on each coordinate we're going to take we're going to fix. So it's kind of like we fix one point here, and then on each coordinate we take the complement. So if we in the first coordinate we had 0. This is going to be 1 and 2.
Excuse me, what are you doing now? You're giving the proof?
No. I'm giving a definition right now, just a definition. And I haven't finished. So right now I'm just defining gamma. And now I want to define. So subcover of so right now this is the main thing I want to define. So I take I have a cover that is with sets of this form, and then I take a subset of this finite. It's very important that it's not 0, 1, but 0, 1, 2, and we'll see. We'll see later. And then this is kind of measuring the smallest, the cardinality of the smallest subcover of sets of this form that cover S.
But can you explain this notation IZC? So let's say that I of some small set is 0. This means I'm allowed to put 1 or 2. What is this notation?
So I is like so. For example, I is like okay. So let's say. It's 1, 2, 3. Okay, and I is kind of like, okay, to 1 we assign something like, say, maybe not 1, 2, 3, let's call it ABC. And I is kind of like a point, it's kind of like a word.
Wait, Z is a subset of the natural number.
Okay, yeah. Okay. I just don't want confusion with the.
So 4, 5, 6.
Yeah, 4, 5, 6. Yeah. Okay, so I is kind of determined. It's kind of like a word. So I is like, I don't know, say 0, 0, 2. And then I defines an open set that is everything that has like a 1, 2, 1, 2, and 0, 1. So all the possible combinations, like 1, 1, 0, 2, 1, 1, these possible combinations, these are open set. And now what I want is the cardinality of the smallest subcover of S using only sets of this type. So think of this kind of sets as a family, and now I just so this is the lemma, the main lemma. Okay, so now this is the combinatorial lemma.
I have a very silly question. So the Z and the Z with the bar in the middle, that's still the same Z, isn't it?
This one is a member of.
No, I mean here, there's capital Z and capital Z with a bar in the middle somehow. So
Sorry.
it's still the same. Because second I'm having two Z because
I wanted to use with bar as a member. But for this one I just want no bar.
Like 2.
Yeah, that's
the problem.
It can't be substitute too, so I didn't have the problem with this one.
Okay.
Yeah, so my second question is it somehow important that Z is a subset of n and not integers? In the second line, you have the
so I'm just actually this could be a finite set. It doesn't have to be a subset of the integers. The only reason why I put it subset in the integers is because when we apply it, that's where we're going to use it.
This is just a finite set.
Yeah, so I don't know, is it so it doesn't look like a 2.
No.
Because this is a 2. Okay, I'll put it in different color.
And in the exponent.
Exponent, yes.
I'm sorry, I shouldn't have asked.
Sorry. No, it's okay. I mean, some of my letters are confusing.
We all have this problem.
In the
Polish actually it's illegal to put the line because then
No, it's
like
not. It's not illegal. It's not like the police comes at something.
it's trash. Because the z with the line equals z with the point.
Well, okay. Sure.
Okay, so this is the lemma, and it's kind of, I mean, it's, if you look at this Sauer-Scheller lemma, it's similar but not exactly the same. And this other lemma, like the proof is very different. And Hanfeng told me this lemma was the most difficult part in the. So because it's similar to the other lemma, but it was different, and you'll see why we want. So you see why we want sets of this kind there. So I will not prove the lemma. That lemma is more like a combinatorics, but I don't want to tell you how we can make the connection. And why this kind of these covers are
C then is CB, right? In the last line. Well, before we are.
CB, yes. Yeah, so this is kind of, this B is giving you the exponential growth. It's telling you that something is growing exponentially. And then this CB is kind of giving you the independence density. That's kind of like the, so like if there's a connection between independence, like exponential growth and independence. Okay. We want proof of theorem. So I don't have the theorem anymore, but it's the theorem that was written here about the disjoint closed sets, and that they there's equivalence between entropy and so from from independence to positive entropy, I mean, when you have independence, the exponential growth is very evident. So this is not the interesting part, and you can just plug in the numbers and you'll see the so the interesting part is the other direction. And I mean, this is kind of like a straightforward application of the lemma, but we find. So now we are going to code. we're going to. This is the. So the image is a function that goes from here to here. I hope. Okay, let me change. Just to avoid the confusion. So I'm going to define this as I if ds x is I 0 otherwise. So this is how we code. Okay, so we have x, we have the complement of the open set, that is k1, we have k2. So we have, if the point is here, we write 1. If the point is here, we write 2, and if it's in both, we write 0. So just to give you an idea, for entropy, entropy is about measuring the smallest subcovers that still cover. And for example, if the point is here, it can only be covered with the complement of K2. If the point is here, it can only be covered with the complement of K1, and if the point here is when it's we have some freedom. So that's why so that's why this sets. So actually. Let alpha. So this is open cover. Now n alpha n is equal now we see the image. Okay, so this is the image of the orbits. So we have the points. Okay, this will be here f, and think of f as first integers.
So also above, it's a CF.
Yes. So actually, this is exactly, I mean, this is a matter just of like expanding, so the covers coincide. I mean, if you want to cover the section of an orbit, it's the same because we're using the complements here, and gamma is exactly defined with the complements with the complements of the points, like it was defined here. So actually this, like you can see that there's a correspondence between the subcovers of this and the subcovers.
Wait, what is NFX?
This is the image of all the, you're coding here the finite section of an orbit, you're coding it with this procedure. So this is a subset.
Because I don't think you introduced N, was N introduced with the subindex? I don't remember.
This is a subset of here, right? And we defined this number is the smallest, is the cardinality of the smallest cover of this image using elements that look like this, like a complement of points. And this is the smallest cardinality of a subcover of this. So this is. So I mean, they're kind of similar because actually they're the same thing.
So wait, so you now define gamma?
Gamma, I defined it before. Gamma, I said gamma is the sets like this. This defines gamma. Gamma are the sets such that where you fix points and then you take complements on each coordinate and you take a product.
Okay, so this looks just like it's not even a definition. This
is equality.
This equality is just by definition.
Yes.
So this is just like changing the numbers around.
Exactly. Yeah, I mean each definition has its. I mean, but once you put them together, you can see that they're the same. And now, since we have positive entropy, so it means that as n is increasing, this has a size of like some. So for sufficiently large n, we have so we can take a half. I mean, we could take something else, but a half is enough. So this we're just using that the limit of the logarithm of this divided by n is this is the limit. So at some point, this is kind of like it's telling you this is like the growth of the. So then we use the lemma. Because now we have, if we have exponential growth, then there is going to exist J in a subset of F with a large proportion, and this and J is going to see 1 and 2 with like all the possibilities of 1 and 2 that we want. But when do we see 1 and 2? Exactly when we are either in K1 or in K2. So the conclusion of this lemma is that we have this J, but this J is telling us that we're going to see within this J we can see 1 or 2, but 1 or 2 is just exactly means that the point is here, which was exactly the definition of. So we use the lemma to find J. Actually, J is an independence set for K1, K2.
Okay, so I have a horrible question now.
Yes.
Could we try to do this with 3 sets? So we've covered by 3 sets? Then
yes.
somehow define the independent set for a like a triple, not a double sets but a triple, and then define this function phi. I assume we'll be using several different symbols depending on which intersection we are in.
If you increase the set,
Yeah.
then the things are only going to be more complicated. Yes?
Sure.
So if you take the first set being simply the complement of those two, then you get back to exactly the same truth.
Yeah. Okay.
But I think your question is very good and it's not trivial, but with a bit more work, you can get when you have positive entropy, you can find not just K1 and K2, you will be able to find like inside K1 and K2, you're going to be able to find 2 sets such that these 2 sets also have independence. And then in each set you can find other 2 sets. So then you can find like some Cantor, and this is used for some. This kind of results, they have applications. One is, in particular, this one that you say about, okay, can you find more sets? This one can be used to prove there's something called a Lee York chaos. So this can be used to show like positive entropy in many other contexts, like when you have Sophic entropy, or even so there's other notions of entropy for group actions, and you get that positive topological entropy gives you Lee York chaos. And another application was there was a question of when group actions, distal group actions, have zero topological entropy. And for like for dynamical systems, it was known since a long time. But if you want a proof for other group actions, this is kind of the path. This is the techniques you need to use to prove that distal systems have zero entropy. So yeah, this yeah, about finding more. Yeah, so if you want to go from 2 to 3 to more, I mean, this is a relevant question, and And actually, in the other lecture, we will see other kinds of independence. Like this was with positive density, but you can also just ask for like finite sets or finite large sets. There, having pairs, you cannot do this trick. So, like 2 is the maximum you can get sometimes. But here, with more tricks, you can get like you can find other sets. And,
Isn't the proof related to proof of variational principle?
which proof?
I mean, if you have positive measured or entropy, then just, no, I assume it is positive. Then you can shrink slightly the sets and measure theoretic entropy to have them disjoint and some small measure thing which thickens the skeleton of them, and then you obtain topological entropy. So positive in the sense you have trajectories
Yeah,
which are more or less independent.
so I think there could be proofs. I mean, this proof and actually,
This is Mishurevich proof, which I told now.
yes. There are some proofs that can use a measure theoretic approach and use measure theoretic entropy. And this what I'm explaining now, they on purpose avoided any measures. And so so there was this open question for some time whether certain proofs could have a purely, because many proofs in topological dynamics were using measures. And some people wanted proofs that didn't use any measures. I'm not sure why people wanted that.
No, here, the first proofs of variational principle, they use it, this additional set which makes sets measure theoretic entropy to be disjoint. They wanted something which is topologically small, something like this. And they realized that in fact only measure is important to be small, because if you create maybe big diameter, but tiny in the sense of measure, additional set, then measure theoretic entropy does not change much. So you can do that, then you have nice topological picture to create, to observe big topological entropy. So this was Mishurevich.
Yes.
But here everything is topological. So
Yeah, so maybe
I just had in mind this picture, Mishurevich picture. I don't see anything concrete. Just wanted to ask a question.
So yeah, I don't. So maybe there's some ideas there. Probably where other ideas are used is when I define the independent set, I said there exists one point that satisfies your choice. If instead of saying there's one point, you say there's some points with positive measure that satisfy your choices, then there's also a version of this, there's a measure theoretic version of this result.
Okay, but if we want topological entropy, maybe one point with those optical.
Yeah.
No. Okay,
Yeah. Yes, I think that's it.
well, this is in your notes.
Yes. I mean, not the proofs.
No, but check the definition.
Yes. All the definitions are in the notes. Yes. Yes, sir. Oh.
Yeah, so the question is if we go for